In this lesson we'll talk about binomial theorem. Let's observe the powers of binomial. If we raise anything to 0, it's just 1. If we raise this bracket to 1, it is the same bracket, but let's observe the coefficient by x and y. So for the first power of x plus y, we have just 1 and 1. If we square the binomial, we end up with 1x squared plus 2xy plus 1y squared. So the coefficients are 1, 2, 1. And the following third degree power, if we unfold this, it turns out to be 1x cubed, 3x squared y, 3xy squared, and 1y cubed. So observe the coefficients are 1, 3, 3, 1. Very symmetrical. And if you observe the behavior of powers of the first term, it is decreasing. It's 3, 2, 1, and 0. And the powers of y will be increasing. 0, 1, 2, and 3. Let's see if this pattern repeats for the next step. X plus y to the 4, it turns out to be 1x to the 4, 4x cubed y, 6x squared y squared, 4xy cubed, and 1y to the 4. So again, our observation repeats. The exponents for x decrease, 4, 3, 2, 1, 0, and for y increase, 0, 1, 2, 3, 4. Coefficients are 1, 4, 6, 4, 1. Again, very symmetrical from the center. Let's see one more row to see even more clearly some of the properties of those powers. So fifth power of x plus y, the power of x decreases, x to the 5, 4, 3, 2, 1, and nothing. And power for y increases from 0 to 1 to 2, 3, 4, and 5. In each term, the sum of exponents is always 5, 1 plus 4, 2 plus 3. And the coefficients go 1, 5, 10, 10, 5, 1. Again, very symmetrical. If we line up those powers of binomials to form a triangle like you see here, then we can observe some regularity. For example, the 2 comes from adding this 1 and that 1. The 3 comes from adding 1 and 2. The 4 is the sum of 1 and 3. The 6 is the sum of 3 and 3. The 10 is the sum of 6 and 4. So what's happening is the coefficient in the next row comes from the sum of the closest coefficients above. Okay, let's generalize our observations for the nth power of binomial x plus y. The exponents of x should decrease. The exponents of y, the second term, increase. The degree of each term is, if that was fifth power of binomial, the degree of each term was 5. That was fourth power, the degree of each term was 4. So generally, if this is nth power, the degree of each term will be n. And the coefficients come from something that is called Pascal Triangle. That's a triangle of just coefficients from the triangle above. So if we overlook all the variables and addition, we end up with just coefficients. 1 corresponds to row 0 because that was power 0. 1, 1 corresponds to row 1. That was the first power of binomial. And then you have second power, second row, third row corresponds to third power of binomial, fifth row corresponds to the fifth power of binomial. And as I mentioned before, every next row of coefficients is built from the previous rows by adding the closest numbers that appear at the previous row. The other thing that we do to create next row, we add 1 on each side. So how would we create row 6? It will be extra 1 here and there, and then we're adding the 2 coefficients from the previous row to create the coefficient at the middle. So that will be 6. Here 5 and 10 will be 15. 10 and 10 gives us 20. And 15 and 6 again. And 1. So that's the 6th row. If we, for example, would like to find out how much is x plus y to the 6 will use these coefficients and will decrease the exponent of x. That will be x to the 6, x to the 5, x to the 4, x to the 3, x squared, x and nothing, and increase the exponent of y. So no y, 1y, y squared, y cubed, y to the 4, y to the 5, and y to the 6. Finally, we place the addition between the terms. So that will be the formula for the 6th power of binomial x plus y. Now, if we have a minus inside the bracket, then what will happen is every second term will be negative. Why it is so? Because instead of negative here, we could think of x plus negative y as a second term and then raised to the 6, which means every term that involves odd powers of y will be negative. And odd powers of y starts from the second term and then every other term. So the formula for the 6th power of the difference of x and y will have a minus before the second term and then every other term, like this. Let's investigate a little bit closer this Pascal triangle. It has a lot of properties. For example, if we choose any nth row, for example, the 5th row, the k plus first entry in this nth row, for example, if k is 1, the k plus first entry is this one, number 5. And this k plus first entry represents the number of combinations of choosing k out of n objects. So we're claiming that this is really the same as 5 choose 1. Why it is so? Let's observe how do we get the second entry. The second entry is the coefficient by the term of the type x to the 4y. So we want 4 x's and 1 y. How did we get this? If we multiply 5 brackets of x plus y, to perform this multiplication, we really need to multiply each term by each term from each bracket. So to create a term x to the 4y, we need to pick x from 4 brackets and y from just 1 bracket. So the number of choices of one object out of 5 objects is exactly the number of combinations 5 choose 1. Well, let's check, for example, this term. That will correspond to k equals 3 because it's a 4th entry. So k is 3. Therefore, this is coefficient by the term x2, y3. That means that we want to choose 3 brackets to pick y from and the rest of it 2 brackets to pick x from. Again, the number of choices to pick 3 brackets out of 5 is the same as 5 choose 3. And you can check that the number of combinations 5 choose 3 is really equal to 10. Notice that if we want to find out the third coefficient in this 5th row, we need to find number of times that the term x cubed y squared, that's by x cubed y squared, can be obtained when multiplying these brackets. Well, that means that we need to choose 2 brackets out of 5. And from these 2 chosen brackets we pick y, and from the rest of them we pick x. Therefore, the number of choices 2 out of 5 is the number of combinations 5 choose 2. And this is really 5 factorial over 5 minus 2 is 3 factorial times 2 factorial. So after reducing 3 with 5, we end up with in the numerator 4 times 5 and in the bottom 2, which is really 10. So we can observe even something more. We notice that 5 choose 2 is the same as 5 choose 3. We end up with the same coefficients. Well, generally, we could show that n choose k is actually the same as n choose n minus k. You may want to investigate this formula on your own. Prove it directly from definition. Generally, the k plus first entry in the nth row of Pascal triangle, so for example here the third entry in fifth row is 5 choose not 3 but 2. So it's n choose k, not k plus 1, because the first entry really corresponds to 5 choose 0, so k is 0 for the first entry. Therefore, it's good to remember that k1 is really the second entry, not the first. So, generally, k plus first entry in the nth row of Pascal triangle is n choose k, and from the formula, this is n factorial over k factorial and n minus k factorial. So now the entries in a Pascal triangle, which corresponds to coefficient in binomial expansion, are written in more concise way using this Newton bracket. And this allows us to write the binomial formula using summation notation. So the nth power of a binomial is the sum from k, that's our counter, changing from 0 to n, of the Newton bracket n choose k, number of combinations of choosing k objects out of n, times x to the n minus k starting from the highest exponent, and y matching it to n, so y is to the k. When you add these two exponents, the sum is n. So that's a binomial formula, good to memorize and include it in your favorite list of formulas. Okay, let's practice a bit. What's 15 choose 0? Obviously, if k is 0, that's our first entry in Pascal triangle, it must be 1. But let's use the definition of Newton bracket, so that will be 15 factorial over 0 factorial and 15 factorial. Obviously, these two guys will cancel and we end up with 1 over 0 factorial, which is still 1. It's not 0, it's not undefined, it is 1. So that's confirmed. Now let's see what's 12 choose 10 without using a calculator. So that will be 12 factorial over 10 factorial, and 12 minus 10 is 2 factorial. Therefore, after reducing the 10 with 12, we end up with 11 times 12 in the top over 2 in the bottom. So we can cancel the 2, leaving us with 66. So 12 choose 10 is 66. That means that the 11th entry in the 12th row of Pascal triangle is equal 66. And now I will show you this formula that I ask you to try on your own. Well, n choose k is n factorial over k factorial n minus k factorial. And n choose n minus k is n factorial over n minus k factorial as it is, and then is n minus k, so n minus k factorial is actually the same as just k, so this is the same as n factorial over n minus k factorial times k factorial. Obviously, this formula and that formula are the same, so yes, they are equal. Let's expand this binomial. This is 7th power, so let's figure out the coefficients first. That will be 7 choose 0, which is 1, then is 7 choose 1, which is 7, then is 7 choose 2, which we'll calculate in the next row, then it's 7 choose 3, then it's 7 choose 4, 7 choose 5, and 7 choose 6 is the same as 7 choose 1, applying this formula. So 7 choose 6 is the same as 7, and 7 choose 7 is the same as 7 choose 0, which is 1. Now we can think about the terms x and 1. So x will go with decreasing exponents, starting from the 7th power, x to the 7, x to the 6, x to the 5, x to the 4, x to the 3, x squared, x and nothing. And here instead of y we have even simpler thing because it's just 1. So multiplying by 1 won't change anything, no matter which power of 1 we'll take. So those are the terms. Now we need to decide about sign. Since this is a difference rather than sum, Starting from the second entry, every other term will be negative, and the remaining terms are positive. So that will be the expanded form of the 7th power of x minus 1. Obviously, we could write this in more concise way using sigma notation, and that will go with k equals 0 to 7. And the coefficient that we use is 7 choose k, and then it's x to the n minus k, so it's 7 minus k. The only thing is we need to accommodate for the sign, so we'll use -1 to certain exponent. Every second term needs to be negative. So if we use k, if k is 1, which corresponds to second term, that will give us a negative sign. So that's a good formula. Okay, now let's try to do the same using sigma notation, the 6th power of this binomial. So it's a sum, big sigma, from k equals 0 to 6, and then think about coefficients. That will be 6 choose k, and the first term 2a will be raised to the 6 minus k. However, the second term, which is b squared, will be raised to the k. And then if we want to really unfold and see explicitly each term, we need to plug it in k equals 0, 1, 2, 3, 4, 5, 6, and calculate each term and record it. But we can leave it in a more concise way using sigma notation. In the next exercise, we want to find the exact term, the 5th term of the binomial expansion of this expression, 15th power of x to the -1 minus x squared. Well, the 5th term corresponds to k equals 4, not 5. Maybe first expand this binomial using sigma notation, so that sigma, where k is from 0 to 15th, the -1 will be to the k because of this negative. Then we'll have 15 choose k for coefficients, and then we'll have x to the -1 to the 15 minus k, and times x squared to the k. So that's entire binomial, but we need the 5th term. That means the term of the sum when k is 4. So if k is 4, we have rewrite the whole expression using 4 instead of k. So it's -1 to the 4, 15 choose 4, x to the -1 times 15 minus 4 is 11, so -11, and x to the 2 times 4, which is 8. Okay, let's try to simplify that. -1 to the 4 gives us the positive term. 15 choose 4, you can use your calculator and evaluate this combination. It should end up to be 1365. Check on that, please. And then combine the powers of x, so that's really x to the -3. Okay, so that's the 5th entry in our expansion. In the next example, we want to find the middle term in the binomial expansion 3x plus y squared to the 8. So if this is 8th power, how many terms do we have? We have 9 terms. Because remember, the counter k starts from 0, ends on 8. So from 0 to 8, we have 9 terms. Since we have 9 terms, the middle term, so the middle term is the 5th term. Therefore, k corresponds to 4. K is always one lower. Okay, as soon as we know that k is 4, we can find the middle term first by writing general term, which is 8 choose k, first term 3x to the 8 minus k, and then second term to the k. So if k is 4, we have 8 choose 4 times 3x to the 8 minus 4, which is 4, and y squared to the 4, which after simplifying we can figure out what 8 choose 4 is, either by hand or by using a calculator. This turned out to be 70, and then we have 3 to the 4, which is quite a lot here, x to the 4 and y to the 8. Now using your calculator, 70 times 3 to the 4 is 5670, and then x to the 4, y to the 8. So that's our middle term. And the last example, use binomial theorem to find the value of 2 plus 3i to the 4. Well, that's a great application. Now we can recall complex numbers because I is the imaginary number. Remember, I squared is defined to be -1. Multiplying complex numbers, it's not so quick, especially to the power of 4. But binomial theorem should help us to do it more efficiently. Okay, this expansion should be sum from k equals 0 to 4. And now we have the Newton's bracket. 4 choose k. First term is 2 to the 4 minus k, and second term 3i to the k. Well, let's unfold this. If k is 0, then this Newton's bracket is 1, and this factor becomes 2 to the 4, so it's 16, and that factor is something to 0 is 1, so it disappears. Second term, plus, if k is 1, 4 choose 1 is just 4, times 2 to the 3, which is 8, and times 3i to the 1, so it's 3i. And the next term, when k is 2, 4 choose 2. You can recall from Pascal Triangle, or you can calculate very quickly on the side. 4 choose 2 is 4 factorial over 2 factorial times 2 factorial. So it's really 3 times 4 divided by 2, so it's 6. Okay, so for this term we have 6 as a coefficient. Now 2 to the 4 minus 2 is 2, so it's just 4. And then 3i is squared. 3i squared. Okay, now if k is 3, 4 choose 3 is the same as 4 choose 1, so it's just 4. 2 to the 4 minus 3, which is just 1, so it's 2. And 3i to the 3, 3 to the 3 is 27, and I to the 3 stays. Plus, finally, if k is equal to 4, then 4 choose 4 is just 1, so we don't have any extra coefficient here. 2 to the 0 disappears, and 3i to the 4 is like 3 to the 4, which is 81, times I to the 4. And what's left to do is to deal with the i's. So we have 16 plus 4 times 3 is 12, times 8 is 96. I. Next, since this term involves I squared and I squared is -1, so this overall term becomes negative, and we have 24 times 3 squared, that means times 9. You can use calculator. 24 times 9 turn out to be 216. So no i's anymore from this term. Now I cube is like I squared times I, so it's -I. So we still have a negative. And then we multiply 8 times 27, and this turned out to be 216 again, I. And I to the 4 is back to 1, so it's just simply plus 81. Finally, we can collect like terms, and we have 16 plus 81, which is 97, minus 216. That turned out to be -119. And 96i minus 216i becomes -120i. So this fourth power of our complex number 2 plus 3i is -119 minus 190i.